Hi there. My name is Jane Tang. I'm a principal at Bootstrap Analytics. Today, I want to talk about how we could use Kalman Filter in brand tracking. This talk is based on these two papers that was presented at the Advanced Research Techniques Forum. The first paper is from me and my colleague Andrew Granville and my friend Karen Burrows. We presented this paper, Fly Me to the Moon, the application of Kalman Filter to tracking data at the Art Forum in 2016. My colleague Jack Horn and I again presented the second paper, Sampling the River Twitter and the DIY tool for social media tracking via the REST API at the Art Forum in 2017. So, talking about Kalman Filter. Kalman Filter was first introduced into the Apollo space program. When we think about these two things, the space program and brand tracking, what are some of the common points? Why are we using Kalman Filter, which is really is more an engineering type of methods to brand tracking, which generally more have to do with statistics. The basic idea is to say that in the space program, we're following the spaceship and we're trying to determine the trajectory of that spaceship and that trajectory follows a smooth path. And this is similar to what we're doing with the brand tracking when we're measuring a brand's performance, a brand perception. That trajectory is smooth. Brand perception don't jump from one point all of a sudden to the next point. There is a smooth trajectory in behind our sampling. Then that brings me to my second point is even though that trajectory is a smooth trajectory, we don't actually observe that entire continuous change in that trajectory. What we do have is periodic observations. So the astronauts take periodical observations about where they are, where the spaceship was, and we took periodic samples in about where the brand is sitting in terms of perceptions in the consumer's mind. And that's the third point here is when the astronauts taking measurements about the spaceship, there is a random measurement error associated with the statistics they just recorded. And the same thing with us when we're taking brand tracking measurements from the sample is there is an error component associated with our measurement, whether it comes from sampling error or some other kind of biases, but there is a random measurement error associated with it. So what we need is essentially a fairly simple and flexible tool to optimally separate the signal from the noise in the data. This is true for the space program. When in the Apollo program, they had a very primitive computer. They don't have the same power. These computers did not have the same power as they do today. So they needed something fairly simple and easy to implement. And obviously for us, if we could get something simple and easy to implement, why not? So how does Kalman Filter work? This is the basic equation. This is the basic equation. The equation at the top is saying an estimate of the measurement that we want at any given time t is a weighted average of the measure we took at time t and the previous estimate that we have at time t minus 1, whatever these period might be. And you can see there's an immediate advantage for this formulation because all we really need is the current measurement at time t and the estimate from the previous time measurement from time t minus 1, we don't really have to worry about all of the prior measurements that before time t minus 1. So time t minus 2 is irrelevant. Whatever the information that existed in time t minus 2 is already incorporated into the estimate at t minus 1, so we don't have to worry about it. So it's this very elegantly incorporate all of the prior information that we have to date. So the way this works is we separate out these two ideas. One is the state equation. This has to do with the movement of whatever thing you're measuring. In this case, we're saying the movement is assumed to be stable. So we're saying the current measurement is equal to the previous time estimate at t minus 1 plus a random error. And this random error is then distributed distributed normal with a mean of 0 and a standard deviation of q. At the same time, we realize there is a measurement error associated with any measurements we take. So we're saying any measurements we currently have is actually composed of the true state of the measure, which is xt, plus a random error at this time as well. And in this case, the random error is also normally distributed with a mean of 0 and a standard deviation of r. So in practice, what we have is essentially these two separate updating equation in our random walk model, basically essentially saying we have a stable state. Because we have a stable state, meaning whatever the statistic would intend to measure is not currently moving away from its current state, then what we're saying is there should be a very small external shock. So in this case, the value of q, we cannot set it to 0, but we should set it generally to a very small number instead. And we go from these updating equation iteratively to update to the next time period. This is easier to explain if we just look at a numeric example. So we do have to have a starting point, and the starting point in this case is x0 and p0. And for these numbers are somewhat arbitrary. I put an x0 number I just set it to 0, and the p0 is set to 1. And these, like I said, these are somewhat arbitrary. I put p0 a slightly larger number. In this case, I said it's to 1 because what I would like to do is, knowing that my x0 is essentially completely arbitrary, I would like to place more weight on that very first observation that I'm going to take in. In this case, I put the q, which is represent that external shock standard deviation, to be 0.001. And I put r to be 0.1 is essentially the best guess I have about the measurement error. So in this case, I think the measurement's going to have an error, standard deviation about 0.1. So when you put these number in, you can see these equation just updates iteratively for every observation I have. So at point time t equal to 1, I observed a number that says 0.39. Putting all of these number into that equation, I have an estimated value of 0.355. And then in that time time period number 2, I have an observed value of 0.5. these equation works out to give me an estimate of the number to be 0.424 at time period 2. So this just goes on as I have more observation come in. And what does this look like? If we just charted, this is what it looks like. The blue dots are what we actually observed about the system. In this case, the true value is actually 0.4. The observation we have is goes right around 0.4, indicating it is a stable system. The mean out of these 10 observations I have is just under 0.4 because there's always a measurement error as well. So what the Kalman filter did is essentially pulling all of the observed value closer to the mean. So it smoothed out the big jumps and gaps that we see in the observed value, pulled everything closer to the mean, and then that becomes a better estimate of the actual value of the system at any given time period. So what is the impact of that measurement error? Remember, I assumed that the measurement error for the orange line here was 0.1. So what if I was wrong? What if the actual measurement error was actually much larger? What if it's actually 0.5? So in this case, you can see the impact of having that 0.05. In this case, you see that blue line. Sorry, not the blue line, the gray line. The gray line itself also smooths out the extreme value in the observed data. But on the other hand, it's saying I don't trust the observed value as much. I should be relying on my previous estimate more. So it converges to the mean, the true state, slightly slower, but it does more of the smoothing. And creates a bigger impact of that smoothing. It has a bigger smoothing impact. Here it's slightly different. What I did is I arbitrarily rearranged all of the values. So instead of having this random observation errors, what we're saying, what if there's actually a trend in the data? What if the trend is going up? So I observed this monotonically increasing line in the blue line. The mean doesn't change because it's just the mean of the 10 values, but the Kalman filter is picking up on that trend to say, okay, well, there's something is actually happening as the new data comes in, we're actually moving up. So in this case, well, what I'm trying to illustrate here is you could use a Kalman filter to reflect that trend in your data if the trend is actually there. So how do we use this in tracking data? In truth, I hate tracking data because quite often there's so much noises in the data, I really couldn't tell the good story. So in this case, these are there's two charts from an actual tracking study where we tracked the brands for 6+ years. These are we track them twice a year, and these are what the numbers look like for percentage people who are likelihood to recommend each of these 6 brands, as well as the percentage people who pick the brand as being their favorite for these 6 competitors. If you squint really hard, you might be able to say, okay, perhaps brand competitor 5 is gaining ground as it moves up. Brand Brand 3, on the other hand, is stabilizing. It's not going up. It's not going down for the likelihood to recommend. Is for the my favorite brand is competitive number 1 losing steam. You have to squint pretty hard to look at those charts to be able to make those conclusions. And so I would like to see if Kalman Filter would help us clarify the story. So if the goal is to look at trend in movement, the very first thing I did here is I essentially benchmarked everybody to their very first measurement. We created these ratios to the baseline measure, so everybody starts with 100 on the left. So and so the trend is clean, much cleaner. So in this case, we do see the just all of the brands are generally shifting up in terms of their recommendation rate. We see a much bigger. We see these jumps for both competitive brand number 3 and 2 and 3 in year 2.1 and 3.2. So what does that mean? Are we truly seeing these big jumps, or are we essentially seeing more of an abnormality in the data? So what Kalman Filter does is it essentially helps us smooth those extreme value out, so that the chart on the right-hand side would be much easier to see that trend. One thing that I have noticed later on is I actually started the Kalman Filter smoothing with a value of 0 as my x0 value. So that's why the chart on the right, instead it should have started, I think I should have given it a starting value of 100 because I based everybody to 100. But that's why you see the starting point for the right on the chart to be lower than 100, because I did not give it a very good starting value, but still it's working. It achieved its purpose of smoothing out those extremes. We can take a good look at just brand 2 and 3, and you can see how the Kalman Filter smooths out those extremes. We can do the same thing for the favorite brand measure. After indexing everybody to their baseline, the chart on the left looks really like a big mess. But once we smooth that out on the right hand, it's much easier to see what was going on. So in the case, that one little abnormality in the second observation for year 2 really is just an abnormality, and competitive brand number 4 is actually doing quite well in terms of being chosen as the favorite brand. So again, you can see how what Kalman Filter is doing, trying to soften that extreme. So one of the things that I just want to point out is, how would we normally have dealt with situations like this when you see these big extremes? What we tend to do in a brand tracking is use some kind of running average measure. But that, again, that's somewhat arbitrary. Why is it better to have a 3-month rolling average, or 3-point rolling average versus a 2-point rolling average or a 5-point rolling average? Some of that is a very much an arbitrary decision, and in this case, the Kalman Filter essentially simultaneously taken care of that. You don't actually have to previously decide how many points we need to roll to create that, because that measurement error accounts for is accounted for within the Kalman filter smoothing. Another good application of this is using the Kalman filter directly applied to social media data. So in social media data, there's a lot of jumps and extremes. When you use Kalman filtering, it just helps you helps you see that picture a little better. Here's another example of Kalman filtering. In here, we actually had weekly tracking data for a brand who is an Olympic sponsor. So we tracked the brand before, during, and after the Olympics, just to see how much lift the Olympic Games was giving this Olympic sponsor. So in this case, I plotted the observed value, which jumps all over the place. The 4-week rolling average does some of the smoothing job a little better, but the Kalman filter gives you a much cleaner picture to see how much of that is actually how much of the lift we got during the Olympics, and how quickly it came back down after the Olympics. Another good use of Kalman filtering is to be able to use Kalman filter to incorporate known system instability. So quite often when we run brand tracking, we would know when there is an issue with the company's brand, or the company is doing a push about the brand awareness. So we know there are times where the company is trying to improve the brand's image, or there's some unfortunate event that happened that the brand image might suffer for that brand. So if we know these additional information outside of our brand tracking data, can we then incorporate the type of additional information into our brand tracking through Kalman filter? So in this case, this is still the same example I used before, where we had 10 points of observation. However, in this case, I have prior knowledge. I know there is a shock to the system. Something is happening to the system that could potentially cause a change in time of 5, 6, 7, and 8. So in this case, instead of holding that Q variable, which is known to be to account for that system shock at a constant low level, it was at that constant low level of 0.001 for period number 1, 2, 3, and 4, but I increased that Q value to 0.005, essentially 5 times as much in period number 5, 6, 7, and 8. And then it went back to the low shock value of 0.001 again in 9 and 10. So what happens when we look at this Kalman smooth results is that in 5, 6, 7, and 8, because I know there is a system shock, and potentially I should trust the observed value more. So instead of smoothing away like the gray line was, the blue line essentially saying we should trust the observed value more. It pulled away from that smoothing during this time when I know there is that system instability at that time, and then off it goes afterwards. So how does this work in real life? One of the things we know is that we all do social media monitoring for our brands. If the idea here is if you do social media monitoring, at time when there is a huge buzz around the brand in your social media monitoring, we would expect there is potentially a higher probability for the brand attribute itself to change more. So in this case, the buzz is proportional to the volatility around the brand equity. So in this case, what we did is we monitored the number of tweets that had mentioned Trump in the first 6 months of 2017. And we're saying is we could use these buzz number, incorporated into that value of Q to improve our brand tracking of Trump's approval rating. And that's what we have. The orange line in here is the raw number coming from the brand tracking in terms of his approval rating. And the gray line is if we had held the Q number, the buzz number constant. And the blue line is if we had updated that Kalman filtering with the Twitter mentions. So in this case, it's not a huge change, but the impact is visible in terms of his approval rating. So that's the total sample, and this is what happens when we have a smaller subgroup. We did not have nearly as many females from the Midwest to get at his approval rating. So when we applied Kalman filter to it, we do see a bigger impact in that. So I think that is it. Thank you very much. I welcome you if you have any questions.